So where these kinds of networks tend to be really useful is where we've got uncertainty about how objects are actually classified into one class or another class. And let me give a practical example about this using letters. So if I put the following letters up here on this whiteboard, you'd probably recognize these as all variants of the letter lowercase a. That's fine, and as a human, that's your kind of internal reasoning and your own brain kind of flipping into gear and recognizing these via perhaps rules around that each A contains some kind of a loop with a little tick at the end. But then you notice this kind of variant of an A looks completely different from, say, these four variants. And the presence of a slight tick at the end makes these two A's look similar, but is somewhat different to this one, which ends in a straight line. My point with this example is to just show to you and reveal that it's actually incredibly difficult to program a computer to try and do this, because we ourselves can't actually come up with a rule that would actually separate these A's. If you were trying to write down a recipe for someone, say a child who'd never written an A before, how would you instruct them to write this character? And at what point would they have actually got it incorrect? Looking at these A's on the board, they're all recognizable as a lowercase letter A. But if you were grading them as variations of an A, which one would be the best example of a lowercase a? This is the difficulty of certain problems that exist in our world. Another example might be actually classifying objects. And so here we have two cups. One is a glass and one is made of plastic. Now looking at these, you can recognize the difference between these two and probably recognize that this is in fact a glass and this is in fact a plastic cup. But to try and instruct a machine to do this, what kinds of rules and decisions would you actually provide it with which to actually differentiate these two objects? We know that we could have perhaps size. This is a very large glass and these are actually small. But we know that we can actually get glasses that are actually small in size and we can get plastic cups which are much larger. And so that's not something that is necessarily going to generalize. Both are transparent and so we can't rely on that feature to differentiate these objects. So in fact what we do is when neural networks step into these kinds of challenges, we give them lots of examples. So in this particular case of, say, learning letters, we might actually feed into a neural network lots of examples of what an A is and in fact what an A isn't. We're going to give it lots of examples to train on to try and recognize latent features about this A character that the machine itself can begin to model. Let's give an example here that actually doesn't rely on letters but instead relies on media objects. So what I've got here are 3 inputs and 1 output. The output I'm giving here is actually related to whether this song should be actually included on, say, our best hits playlist. So say we're trying to create a playlist that will be the best party playlist that we could ever actually come up with. The 3 basic pieces of information we have of our music is the rating that we've given it within our playlist out of 5 stars, the length of the song, and the genre of the song. These are the 3 basic components we have of the actual song itself. If we're trying to come up with some way to classify songs and say whether they're going to be included or not included in our playlist, then we could perhaps try and use a neural network to try and learn this. And what is it about these 3 variables that makes us more likely or less likely to include them on a playlist? Now to do this, we're not going to expect the computer to do it straight off the bat. Instead, what we might give it is a series of inputs and indicate whether this is included or not included in our idea of an ideal playlist. And so let's start with some rating information. So if we take a song that has a rating of 4 stars, has a length of 3 minutes and 50 seconds, and the genre, say, is hip hop, we might say, yes, this is included in our playlist. Then we give another song which has a rating of 4. Its length is 7 minutes and is also a hip hop song, but say that this is not included in the playlist. Looking at that example, you could perhaps try and make some kind of a supposition that, in fact, it's the length, and that this song, because it is 7 minutes long, is inappropriate for our playlist. Now that's okay on that single variable, but we know that creating an ideal playlist for a party is a bit more complex than that. And in fact, it's the interaction between these various pieces of information that lead us to perhaps including or not including one of these items in our playlist. If we were to then enumerate this list down across, say, hundreds and hundreds of songs, we could actually use these as inputs into our neural network and try and get it to actually figure out what are these actual latent variables, or these connections that exist between variables that allow it to pick whether it's in the playlist or not. The process we do this with is called learning and training. So in fact, what we would do this practically, and how we would actually put this into our neural network is, and if I use our circles again in our neural network, is to have our various inputs. So this would be the rating, the length, and the genre. These inputs would then feed through multiple layers of our neural network with various connections connecting across various layers until we actually arrive at some output. That output there, we're then looking to see whether it's actually high or low, yes or no. Feeding through this information here, what we rely on is what's up here. We call this training data. The idea that we've actually already made an assessment as to whether this song is included, and in fact this song is not included. And so that's the exact information we present at the front of that network. So what we do is we actually take one of these examples. So let's take this first example. We add the rating in there. We modify this to perhaps just be seconds. So that representation in seconds is 3 times 60, 180, plus 50 to be 230. So we put that in as seconds. And the genre, we code that perhaps using some other number. So let's say hip hop, we assign that the number 1. Feeding that information through, we then look at the output and assign perhaps a threshold and say, well, if it's above this number, we're going to include it, and if it's below that number, we're not going to include it. So say if it's above 1, we might include this. So let's say in the output here, we get a number that's actually negative, -2, which we decides that, no, this song should not be included in the playlist. But we know that this song should be included in the playlist because that's what we decided originally within our training set. So in fact what we do is we take that wrong value there and use that information to make adjustments to those weights. Remember all the way back to those little weights that sat on the side of our perceptrons. They're sitting at every single point going into these various perceptrons through our network. So what this means is we can actually adjust them, and by adjusting them, perhaps try and force this into the yes condition. So we make that number by adjusting the weights inside there a positive number above 1. Let's say it's +3, in which case this is correct. These values have led to the playlist saying, yes, this song is included in this playlist. And so we know that that neural network can make a correct classification of that particular song. Now we might actually present it with another song. So let's take this song here. It's also got a rating of 4, so that value is the same. Its length is longer though. So instead of 3 minutes 50, it's actually 7 minutes. So if we do the math on that, that is 7 times 60, which will be 430. We feed that value through, and in fact, look at the end here and look at what number comes out. Let's say this number comes out at 0.5. So that's below our threshold, right? Remember we set a threshold of saying 1 and above is yes, it's included. Anything below 1 is not included. And so in fact, it's classified that one correctly. Had it not though, we could actually go back through and make more adjustments to those weights. And this is exactly what training a neural network does. It's actually going through making modifications to those weights inside the middle until such time as it can actually classify the majority of these media items correctly. And once we've actually exhausted through that data set multiple times and are making no more improvements to the overall accuracy, we call our network trained. And so often when we're talking about the quality of a neural network, we'll talk about it in terms of the accuracy of its classifications. Numbers say around 95% accurate or something like that, to suggest that 95% of the time it might actually be able to take an already a media item here that's already been looked at and decided yes or no that this should or shouldn't be included in a playlist of this type, to decide yes, it should be or shouldn't be in fact included. So that's a brief tour of what a neural network does. They're used within a lot of different media systems right now, from sorting through your Facebook newsfeed and deciding what might actually appear at the top, through classifying images and objects that are fed into the machine to decide what in fact is present or not present in an image. Basically what it comes down to is quantifying data at some level, being able to feed that through some kind of neural network that can be trained over multiple instances of that data where we know what output we're looking for. We can adjust then those particular values to make sure that the input matches the output that we expect, and then we actually release that neural network on some other kind of data set to classify it. The problem with this approach though is that within the internal parameters and such we create for this network, we can't readily get out of that an idea about why certain objects are being classified as A versus B. If we return to our glass versus plastic cup example, we could train a neural network to tell the difference between, say, these two items, but we couldn't actually get back out of that neural network an idea why it classifies, say, this as a plastic cup and this as a glass cup. That's one of the things that we lose in using neural networks, is an ability to theorize about why these objects sit in different categories. Instead, it just works. And so this is a very data-driven and data-centric approach to classifying objects.